Hello, my name is Minjae Lee. We will learn about transport of carriers in this chapter. The transport means the movement of carrier, right? There are two mechanisms to move carriers. So far we had learned about the carrier kinds. One is electron and the other one is hole. So two mechanisms are drift and diffusion. So drift is something like you can imagine a dust. If the wind is blowing, the dust will move, right? So it's a similar mechanism. Instead of a wind, we will see some electrical field, right? Electrical field is applied to any charged device, charged element like a hole or electron. It will move according to the electrical field. The other one is diffusion. Diffusion, you can imagine if you drop a ink into water, the ink will be spreaded out because a different concentration will be quickly spread. So it try to equalize the concentration. So you can imagine such mechanisms. So drift and diffusion. So we will see one by one how exactly those things can be explained in the semiconductor. The first, drift is movement of charge carrier due to electric field. So you can imagine it's like a wind. So if you apply the voltage across the semiconductor material, where some inside there some charge carriers there, either free electron, or the hole, free hole, then this symbol is voltage source, plus minus, like this, right? We had learned from basic circuit theory. So if we apply the positive voltage, so this is a higher voltage and lower voltage, for example 0 and let's say 1 volt, something like that, then the voltage difference will create electrical field. This is some kind of a conductor here. So if we have a large electrical field there, the carrier will move. So if the stronger electrical field applied, the carrier will move faster. So the velocity of carrier can be found by the electrical field proportional. The velocity is proportional to the electrical field. Now, depending on hole or electron, its mobility, we call this proportionality factor, mu. This is called the mobility. Electron mobility, mu n. So mu n is electron mobility, and mu p is hole mobility. So those mobilities are different. So for apply the electrical field, for electron, for example, that will move against the direction of the electrical field because that is a negative charged carrier. On the other hand, the hole will move along with the direction of electric field. So hole velocity is mu p times electrical field E. Now once we found the velocity, we can find the total current density. So J total here is the whole current density plus electron hole density plus hole density. So we know the velocity, so we can multiply with the the charge, amount of charge is, so first N is the electron concentration in unit volume. So each electron has the charge of Q, so Q times N is total. This is the charge in the unit volume, right? And also P times Q is the number of hole in unit volume. So P times Q. Each hole has a Q charge, so PQ is the charge in unit volume, total charge in unit volume. So unit current, so current density can be written like this and total like this. So the Jn here denotes the current density. This is defined by the current passing through the unit cross section, because we are talking about the unit volume. So if you use the number, then we can find the current density like this. So that it will be expressed in A over ampere over centimeter square, right? This is a pretty simple equation, right? The second mechanism is diffusion. So diffusion, if we inject the carrier, let's say we have a semiconductor material here. If we inject the carrier, either electron or hole, to the one side, then the lots of electron or hole, so-called carrier, will be accumulated here. It will have a high concentration. Since we have a lower concentration on the right hand side, so the carriers will be rolled over to the right. So overall concentration will be like this. So we are keep injecting carriers. We are injected carrier like this. It will be naturally spread it over like this, right? What if if the this kind of a non-uniform concentration is happening, and let's say if we take out the carrier from the other side and we keep injecting one side, then this kind of a non-uniform concentration will be steady state. At the steady state, we are injecting carrier at the same rate, and the carrier coming out on the right hand side will be at the same amount of same number of carrier will be coming out. Then the steady state profile will be like this. Now let's find the current out of this concentration. So if the concentration is formed like this, we know that the current is proportional to gradient of the concentration. In this example, electron, so N is the electron concentration. So this will be, current will be proportional to the gradient of the concentration, and also the area, right? If the area you are injecting carrier is larger, then you will get the larger current. And also, if you have a larger amount of a charge out of a carrier, then you get the larger current, right? So this kind of proportionality can be found. So overall, this kind of diffusion, so diffusion characteristic determined by the different material. So we introduce the diffusion constant, dN. So for electron, 34 centimeter square per second, and for hole, 12 centimeter square per second. So diffusion constant is different for electron and hole. So we can see that electron can diffuse better, right? So the current will be I equal AQ times dN, diffusion constant, times the concentration gradient. So if you represent that with the current density J, then we take out the area. So Q dn over dx will be current density from the electron, and the whole current density will be similarly minus Q dp over dx. The total current will be like this, adding those electron and hole current density. So like this. Keep in mind the polarity will be like this. So electron, so the, let's say, current will flow, for example, like this kind of gradient. Electron, let's say, moved like this, the actual current is to the left, right? Yeah, the opposite to the actual electron movement. But if you take the gradient of a concentration, it will give us a negative number, right? This will give us a negative number. So actual current direction is opposite to the electron movement, okay? For the hole, similarly, we know that the dp, if the dp, the p concentration of the hole is looks like this, shown in here, then similarly the electron hole will move opposite direction of this concentration polarity, right? In this case also the minus polarity, right? So but the actual hole and electron hole movement is the same as current and direction, so we have to take the minus here, right? Okay, the minus give us positive, right? Times this becomes positive, okay? Let's do some exercise. For example, if we in the inside the semiconductor, we have the linear concentration like this, linear variation of concentration. With the dimension of the L is very small, so we can easily approximate the concentration difference is the linear like this. So if the injection of the carrier is happening here, and then gradient concentration would be, let's say, initially the concentration at the boundary is, let's say, N, and at the end of the semiconductor, let's say L, the position L, we have the concentration goes to 0, and then we can find the current density. The equation is dq times dn over dx. So here the slope would be minus, that would be what? Minus n over L, right? This is the dn over dx. So we plug that into the equation, we'll get the like this, right? So actually the semiconductor, if the dimension is a lot very large, then the actual concentration will be like a gradient. It will be following the exponential gradient. But if the dimension is so, let's draw it again. So if the dimension, the actual n, so you have your semiconductor. Let me draw differently. So you're injecting the carrier like this, and then you plot the concentration. It will be like exponentially decaying to the end, right? But if the semiconductor dimension is very short and narrow like this, the concentration will quickly drop like this, right? So the electron coming in and coming out immediately at the output will diminish to the zero. So this diffusion current can be easily linearized in here. Okay, this is just example. This is L and this is L. So far we just explained the two different mechanisms of moving the charge, moving carriers. So one is a drift due to the electric field, and the other one is a diffusion by the concentration difference. So all those two have some proportionality factor. One is mu in drift current, and the other one is diffusion constant d. So surprisingly, the relationship between mu and d has this relationship. The d over mu equal kT over q. So kT over q is thermal voltage, Vt. This value happens many places and many times. You must remember for circuit designers. So this kT over q, 26 millivolt at temperature, room temperature 300 Kelvin. Okay. So we will abbreviate the kT over q. Later on, we call it like a Vt. This is thermal voltage. Okay.